You may take a seat. I hereby open the session. Madam Doctoral Candidate, the Board of the Conferral of Doctoral Degrees of Utrecht University now grants you the opportunity to defend your dissertation in public. It's a great pleasure to announce your first opponent, who is Professor Soetaert from Utrecht University. Please.
Okay, so dear candidate, first of all, I would like to congratulate you on the work that is presented here. I found it very interesting and very readable also, and also very diverse. And I especially like how you merge field data with experimental data and with statistical and mechanistic models. And I also like the last chapter, where you apply your new knowledge on quite a number of interesting case studies. So the first question I have deals with methodology. And I would like to start with the units that you use in your thesis, which I find a little bit confusing, because you report concentrations both in milligrams per kilogram, milligrams per liter, and sometimes the same concentration in the two units. And so, for instance, if you look on page, let me see. On page 64, you report PW in milligram per kilogram and then also in a milligram per liter. And the difference is almost a factor 100. So can you explain what it is exactly that you have put there?
Yes, when it's used, so the samples are of sediment samples in this case, but it also happens the same for the soil samples. So what is done is in milligrams per kilogram. That's the expression when it's a solid. And what I try to do is when I put next to it in milligrams per liter, that's the equilibrium concentration that I got in the extraction. Because what I wanted there to show is that it was in equilibrium. The concentration, it was very similar to the concentration in the groundwater. So that was the objective why I put it 2 times. It's a bit repeated, the information that I understand it. Normally it's expressed in milligrams per kilo, but that was the idea, to show for example, in the PW is the phosphorus in the water extraction, and that concentration was in the same range as the concentrations in the groundwater.
So the kilogram is the kilogram dry sediment, or is it kilogram wet sediment?
Yeah, the kilogram dry sediment.
Okay, yeah. And then I have another question concerning methodology or terminology, if you want. So what do you mean with topsoil and subsoil?
Yes. So the topsoil, what I referred to was in the first 10 centimeters, with usually also there are the pictures in the page before. So what you can see is that the top part is mainly mixed with organic matter, and then the subsoil, what I refer to is the last from 40, for example, to 80 centimeters, and that the soil changed quite a bit, had more iron oxides, more sand, not so much organic content, and that was the distinction. It's not a very rigorous, maybe, distinction.
But so you have a section in between that you don't talk about then? So
because it's more transition, so sometimes the samples in between were similar to the top and sometimes more to the subsoil.
Okay, thank you. So the next question deals with iron hydroxides. And so you argue that iron 3 hydroxides can be used to remove phosphorus in the presence of oxygen, as they can co-precipitate or absorb dissolved phosphorus. So I derive from that there are 2 processes that can remove phosphorus, and I wonder whether you know information about the timescales in which this removal and also the return of phosphorus can occur for these 2 processes?
Yes, so I focus more on absorption than on precipitation. Of course, precipitation can also occur. And what we saw of absorption is that it happens at 2 time scales, let's say, or at least that what we studied the most was the absorption in the iron-coated sand. That is a subproduct. So yeah, it's similar to this natural sand with the iron oxides, but it's covered with a greater thickness around with the iron oxides. And what we saw is that it happens in a really fast time scale, instantaneously, next to the iron hydroxide, but then it took some time to diffuse to the inside. So that's what had a longer time scale. The fast time scale is instantaneous, and the long one for this thickness of grains, that was more or less 300 micrometers, took a little bit less than 300 days. So that's the time scale.
Yes, but that would be both absorption, and so how would it be for co-precipitation?
Yeah, for co-precipitation, that the Bas van der Grift, that was previous to me, he did more experiments on precipitation. What I understand is that also goes very fast, but it could be that in presence of other, for example, silicates or other ions, that could be delayed or not so fast. But if not, in contact, the phosphate with the oxidation of iron would go fast.
Okay, so then also for the iron oxides, so when the iron oxides are put into reducing conditions, then the phosphorus is normally released. Is this the case, or?
Yeah, so that's what we thought at the beginning, that the iron-coated sand, when it's placed below groundwater level in contact with organic matter, this would start a reducing process of the iron oxides. And we feared that then the phosphate would be released. But what we saw in experiments is that it was not released under these conditions, and we think that the reason is because the iron was in excess. So even though a small fraction started reducing, then the phosphate was still contained. Of course, if the conditions were very, very strongly reducing at one point, everything would dissolve, but not for the natural conditions in which we place the filters.
Yeah, okay, but so I can imagine that there are situations where you do have the release of phosphorus under anoxic conditions. And so my next question is, I am asking whether there's an analogy to the phosphorus shuttle that you have, like in marine sediments where I'm working on. So where you have the organisms that are moving these iron oxides to deeper anoxic layers where the phosphorus is being released, and so you get very high buildup of phosphorus because of this iron shuttle. Is there something similar in the terrestrial world? Or?
Yeah, I think the analogy is similar. What we saw is that they were all microbial mediated processes, because we also did experiments with abiotic, so autoclaved samples, and there nothing happened. So only the chemical interaction was not enough. So it is microbially mediated.
Yeah, yes. So I think the analogy would be that the earthworms would also do similar things, but they don't.
What you mean, the worms?
The worms, yeah, the earthworms. So
we haven't looked into worms so far.
Yeah, okay, so then my next set of questions deals with,
I'm afraid I will have to pass the word to the next opponent. Thank you very much, Professor Sittard. Your next opponent is Professor Smulders from the University of Leeuwen, and thank you very much for coming over to question the candidate.
Dear candidate, I enjoyed reading your PhD. It was nicely summarized. I like it when it's summarized, of course, for the length, but also it shows that you can synthesize and identify the most important and new things. I also have to say here in public that I enjoyed working with you in the Petra project. You're a nice team player, and but also personal. I always found that you asked the right questions. And you can also think about that. I have a few questions, mostly related to the chapter 5 on the column experiments. The first thing is, yes, alpha, the rate constant, and the fraction of fast sites are important for the outflow concentrations, because the outflow is mainly controlled by the extent of slow reactions. Each sand that we build sample in the field, in the water treatment plant, will require a new column experiment to determine alpha and F. You showed in your work that, in fact, the sorption per unit iron, the equilibrium, is quite equal to what other people found. But if you then take another sand, coarser, finer, do we have to do always a column experiment? Simply said, what would we have to measure to identify the extent of slow reactions in such materials? Is there no such easy thing that you can say, this will determine the extent of slow reactions?
It's a good question. Yeah, hopefully it would be, super easy, it is still. But what I think is that we try to do also to calculate alpha per gram of iron that the iron-coated sand contains. So in that way, maybe it could be related to other iron content in the iron-coated sand. We didn't precisely take into account the size, so how thick the granulometry, the grain distribution of that was not taken into account in the equation. So if a coarser sand would be used, maybe it's thicker, and that would, maybe need a different parameterization, but we think that, for these types of sands that more or less...
Let me interfere. Yeah. If the particles, the sand particles on which the iron is trapped in ICS become thicker, would you have less or more slow reactions?
I think in that case you would have more slow reaction, because you have thicker and then you have more area in which it can diffuse, and also less surface area per kilo, so the fast reaction would be in a lower balance with the slow reaction.
Okay, thank you. Second question. If we scale up the column 30 centimeter to larger, you did 40 centimeter, but in the environment or in operations we can go to meters. And I want to know if there are slow reactions. What do we have to look at? Do we go for the residence time at equal flow rate would of course increase when you go longer, or would we only have to evaluate the flow rate? In your, of course, constant column is flow rate, and the residence time is a column. But is it now the residence time that determines the extent of slow reactions, or is it the flow rate?
Yes, I think both of them determine the contact time that the water with phosphate is with the iron oxides, and that's the time of the absorption. So I think it's a bit of two ways of seeing into the same problem. The way we modeled, what we would use is the flow through velocity, taking into account the area and the porosity, and then the length of the column is also taken into account or the filter is also taken into account in the model. So if the filter had 1 meter or 2 meters, this could be incorporated. I also understand what you say, your point of view is true, that for many practical reasons, when filters are designed, the residence time is what is set as a parameter for design.
The residence times rather than the flow rate, I think. Final question, random forest, maybe a question to be expected. So it's rather new what you did. Of course, nowadays we can all get this at the top of our fingers, these softwares. But yeah, you showed that it's very good for filling the gaps. So there was a day that you forgot to measure, or the machine broke, whatever, and random forest will tell. But what is your opinion on the use of it in environmental science, where you study processes in the environment? So it's a very broad question, but think about it, and what would you do in the future when you go further with environmental science? Should we all use this rather than process-based?
I think it's a very good question, a bit maybe more philosophical or opinion on what to do. I don't think we should discard all our knowledge that we have in geochemistry and all the knowledge we have, because this is kind of a new way of doing models. So it's a database, so the processes are not really integrated. It's only using the data that was retrieved. So I think it's good a combination of both, and to take into account how we understand the processes that happen in the environment, and not only the database models. And that's what we try to show, that if we only use the database model for forecasting, they could not really reproduce what was happening, because it was a changes in processes that they were not captured in the data that we have. And even though we had like more than 50,000 points maybe, that is not enough if the processes are not integrated there. And I think nowadays it's quite easy to retrieve more and more data, because sensors are becoming cheaper and it's easier to have data. But until we have really long data series, it's very important to integrate the process-based approach into the interpretation of what's happening.
Okay, would you dare to give a number, how many numbers you need before random forest are better than regression models? Like, I have a data set of 100 points. Would you dare to go already with random forest? Orders of magnitude, huh? But
No, I think it's really difficult. I think it also happens nowadays, of course it's not my expertise, but for example with climate change and with other things that we measure temperature and rain for over 100 years, and that even has a big uncertainty. Of course in small plots of farms maybe the uncertainty is less, but yeah, I will try to have as much data as I can, so probably more than 10 years maybe, since you have data to be more confident on what could happen.
Okay, thank you.
Thank you very much, Professor Smulders. Your next opponent is Professor Pfeiffer from the University of Bayreuth.
Yeah, dear candidate, I also would like to express my enjoyment that I had reading your thesis, and it stimulated quite some curiosity-driven questions. And my first one is about the legacy P. Legacy P is something that you were addressing quite broadly in your thesis. And you argue that the legacy P, at least at the sites that you were studying, is due to the high PN ratio in manure and compost that is being applied. And while plants, on the other hand, take up preferentially N, and so P remains in the soil. So from a mass balance point, it makes sense. But I understand the agronomists, at least in Germany, and I understand that this is also in other places in the world, that they argue that there is, I have to take off my glasses, sorry, that there's always a surplus P in many soils, but they still have to add P because the phosphorus P that is being retained in the soils is not bioavailable. And this is why farmers need then to add fertilizer. And if this is true, I'm wondering why there is so much P mobilized into the subsurface. And maybe this is depending on the particular sites. But if this has not been taken up by plants on the one hand, but on the other hand it's been leaving to the subsurface, how is this working? Maybe you can elaborate a little bit on this topic.
Yes, thank you. Yeah, what I totally agree. So the main problem is that the phosphorus-nitrogen ratio present in manure is not the same as what the plants need, so that's why the accumulation comes from. Then, of course, the phosphorus present in the manure is in different species, and also many processes happen in the soil. So, yeah, the degradation and microbial processes, and also precipitation processes. So it's true that not all the phosphorus is available for the plants to grow. That is true. But also we have the solubility, and when it rains, the phosphorus that is available, some of it would go to the pore water, and then it would be drained downstream. So that would still happen, being available phosphorus. Some of the phosphorus, also as particles for the soil erosion, would move downstreams. So that still happens. I know that some of the options, I think that are available nowadays, is also incorporating microbes to make more phosphorus bioavailable in the phosphorus that is added. And the other one would be to combine chemical or industrial fertilizers with manure to get a better phosphorus-nitrogen ratio in what is added to the soil, so we don't get this imbalance.
But isn't this looking like a contradiction? On the one hand, I mean, plants are growing only in during the season, and there's winter time. There may be different conditions. That's true. But isn't it a contradiction that a plant is not taking up the phosphorus on the one hand, is not able to take it up on the one hand. On the other hand, there is easy leaching going. Isn't this a contradiction?
Yeah, I think more than a contradiction, I would say it is a compromise. So on the one hand, yeah, phosphorus is needed to make the plants grow, and the more nutrients you have, probably the better plants you get. But on the other hand, that would happen at the same time, that some of it in equilibrium would go into the water, and that would cause environmental problems. So I think, yeah, both happen at the same time, and the importance is, okay, what balance do we make? I get the farmer's point, because probably if they would add more phosphorus, they would get higher yields, and that's their objective. But also, if we want to have all the objectives of global development, as I mentioned, also caring for water quality is also one objective. So I think it's more of a compromise than a contradiction.
Okay, and let's change the topic. So I would like to discuss a little bit about filter efficiency. So we have discussed this a little bit already and identified that the residence time is an important issue. And if you were to design a filter, what requirements do you think need to be clearly stated that a filter has to fulfill?
Yeah. Yeah, so first, I think it would be important to set an objective target of the concentration of phosphorus that we want to achieve outside of the filter. So this is, I think, the most important parameter that would determine the size of the filter and how much iron we would need. So after we know, okay, we want a target of 0.1 milligrams per liter, for example, just an example, of phosphorus, and after that, we could, for example, use the model to determine, okay, what's the velocity requirement? That could be 1, so to determine the area, and also how long it should be.
Yeah, and that brings me back to the residence time or velocity.
Yeah.
It depends on length. And so how long a residence time needs to be? Where do you know this? I mean, you can, of course, you can't expand it to infinity, so to say, but it makes economically no sense.
Yeah, so that is something that we haven't done because it's, we are developing the model. So the main objective was to make the model to describe the processes and not so much to make a table. But with the model, you could make a table, okay, for this concentration, this residence time, you would get this concentration in the outflow, or with a higher residence time, this concentration, and with a higher residence time, a lower concentration. So what the model allows you is to have that table for easy design.
That would be a table, but there's so chemical engineers, they have an approach that they typically use for that purpose. Maybe, aren't you a chemical engineer by training?
Yeah. I did civil engineering, but
yeah. And maybe you heard about the Dammköhler numbers, you know what this is, the concept?
Again, sorry?
A Dammköhler number, have you heard about that?
Not really.
No, okay. So it compares transport times with reaction times scales. And that would be the approach. So you have to know, I mean, you discussed all this in your thesis, so time scales of reaction, and apparently they're quite low. And yeah, and that decides then about the residence time that is required. And that brings me to presumably a last question, because time is running. In your study 5, you because of your findings and the slow reaction of the filter material, so this internal porosity-based reactions, you suggested to allow for some stopped flow once ICS-coated sand is being applied. But I'm wondering, how should this work from a practical point of view, if you would allow for stop flow? How should this look like? So it means that you need to have a filter system and then stop it and wait and then run it again. But that means that the discharge to be treated, that is quite low, isn't it?
Yeah, so
Maybe you can comment on this.
So I think in this case I would separate into 2 types of systems. One would be the natural systems, and in the natural systems I would expect that to happen naturally. For example, in the summer to have less rain, so the system would naturally stop, and that's one of the things that we model. Okay, if for 3 months the evaporation is higher than the rain, and then we don't have any flow through. Or, for example, even in the winter, maybe it rains 1 or 2 days per week. Maybe you don't have water all the time flowing, so that would be natural ways in which the filter would stop. On the other hand, we also have filters made for industry. For example, at the end of a halophyte filter or a wastewater treatment plant, and in that case, I think a little bit more complex system would be needed. For example, to have filters in parallel, the same that is used for drinking water treatment or wastewater treatment. So you have 4 filters, and then one is resting and the other are working, and then you start rotating with a pumping system. But in that way, you allow one of the filters to rest instead of backwashing, for example, for drinking water.
Okay. If I may add.
Okay. I think we have to stop and move on to the next opponent. Thank you very much, Professor Pfeiffer, and thank you very much for traveling from Germany to come to see us today. Your next opponent is Dr. Koopmans from the University of Prague.
Thank you, Chairman. Dear candidate, I also enjoyed reading your thesis, and I think it's a very timely piece of work, especially given the fact that in 2027 we have to comply with the regulations, the standards posed by the EU Water Framework Directive, and that will be problematic, as you will probably know. So that is yet another crisis to happen after the nitrogen crisis. I want to dwell a bit further on the discussion that was already started by Professor Pfeiffer. I want to go to chapter number 2. And in this chapter, you talk about legacy pea soils, and I have a bit of a problem in understanding when a soil qualifies as a legacy pea soil, and even more so when a soil qualifies as a high legacy pea soil, which you do in this specific chapter, because you call it a high legacy pea soil. So my question to you is, why do you consider this specific soil of this experimental farm in the east of the country, why do you consider that to be a high legacy pea soil?
Yeah. So that's a very good question, and that's we also got that question, and we ask ourselves, okay, when is it a legacy pea and when is it just pea that is originally in the soil? So in that case, the farmer wouldn't be to blame if we would like to find people to blame. But what we see, for example, in page 42, is that there were parts that were not used for agriculture in the farm. That is, for example, the point with 340 milligrams per kilo of phosphorus, and that is in front of the house, so that soil was not used, was only used as a garden for the farmer, so manure was not added. And in those cases, the concentration of phosphorus is much lower. And on the other hand, to the northeast, so where the crops are, we can see that the concentration of phosphorus is systematically higher. So all the points are more than double of the phosphorus of the garden. So that phosphorus would be, okay, what was historically added. And we also know that in the farm, consistently manure was being applied for a couple of decades.
Yeah, but if I may interfere, I mean, I completely agree with that. I mean, what you see is that phosphorus is indeed present at elevated amounts. Yeah. But isn't that true for any agricultural soil? Because to each agricultural soil, we add phosphorus in order to reach a certain loading, which means that P availability for the plants is buffered at a certain optimal level. So if you use that as a definition, that means that all soils are basically legacy P soils, right?
If I understand the question correctly, what we were trying to distinguish was from the phosphorus that was originally in the soil, so previously that soil was amended with more manure, and the original soil, P in the soil. That you're right. Every soil with organic matter would have phosphorus because it's a component of the.
Yeah, but also each regular agricultural soil is being fertilized. So that means that any soil will contain an elevated amount of phosphorus. So that would mean, according to your definition of a legacy P soil, any soil will also qualify as a legacy P soil. Why is your soil a high legacy P soil? Why do you give this qualification high to this soil?
Yeah. So I think on the one hand, the target of the farmer was not to add more phosphorus to the soil. So what happened is that the yearly balance was close to zero of what was added and what was harvested. So the difference is what was being accumulated from previously. And then what is high and not high, of course, maybe in some places it's even higher and in some places it's lower. So we try to compare it with some guidelines or standards that were available, and that concentrations were considered high for the standard that we used. But
yeah, I absolutely agree with that, but still, I mean, it remains a bit of an arbitrary thing, whether it is high or low. I mean, definitely it is elevated, but I'm not sure whether I would agree with the term high, a high legacy P soil. But I want to move on to the next question. I want to move on to table 2.4 on page 43. That is where you give the so-called phosphorus saturation degree, which is an important concept that was developed at Wageningen University by the late Sjoerd van der Zee and Willem van Riemsdijk. And I am wondering, why did you decide to calculate the phosphorus saturation degree as the molar ratio of POX versus the molar amount of iron plus aluminum ox?
Yes, if I remember correctly, that was one of the ways to calculate it. If not, we could use the amounts without in molar amounts and then divide it by a factor that I don't remember in the top of my head, but it was 0.5 or something around that, using other units. But then the other way of doing it was using molar values, and then the ratio between converting the grams into the molars would get this factor.
Ah, okay. That would be understandable, because in the materials and methods it says that you only took the molar ratio of POX versus iron plus aluminum, but in fact you should correct this amount of iron plus aluminum. You should multiply this amount with a factor of 0.5, the so-called saturation factor, in order to arrive at the PhD. So that is what you did.
Yeah.
Okay.
I'm sorry if it was not correctly explained.
Okay, well, that helps me to understand that specific part. But now I want to move on to the table that is presented in one of your appendices, because you have quite some appendices. So I thought that it would be correct also to ask a question about that. And I want to move on to page number 64. And in this specific, let me see, in this table you have many different Sol-P tests for which you present the results, but I am very much interested in the PAL value, and I'm also very much interested in the P-oxalate value. PAL is very important in the Netherlands because it is one of the Sol tests that we use in order to classify Sol-P availability in agricultural soils. If I compare these two pools, so PAL versus POX, you see that for nearly all soil samples from all the 3 different depths, including also your sediment samples, PAL is consistently higher than P-oxalate. And you can compare these two because they are both expressed in the same units. So my question is the following one. Given the differences in the extraction solution between the PAL method and the POX method, which of these 2 extractions would have the highest effectiveness to extract P from soil? What would you expect on beforehand?
That's a very good question and a very good point I hadn't thought about before. But yeah, same from the numbers, we get higher values in the PAL extraction, and yeah, maybe beforehand I would have expected to get more in the P-oxalate. That's true. Yeah, that's what I expect, but that's what I see. So here we got more in the.
That is indeed what I also would expect. So I think that is something that you can perhaps look into after when we're done. Let's move on to the following. I want to go to the conclusion section.
Very quick question.
A very quick question.
Yes.
You call the subsoil an iron-rich sandy soil. Why do you call this subsoil, an iron-rich soil material?
So
that's on page 52.
Yeah.
And this is a term that pops up at many places in your thesis, where you consistently refer to the sandy soil as an iron-rich soil. Why is it an iron-rich soil?
Yeah, so now I cannot find where the results are, because you have the soil samples in numbers, but even from the pictures, what you could see is that there were more iron oxides in the part of the subsoil, and in the results we got, there were more in the after 40 centimeters, we got more iron in the higher part, and that's also the main sink for the phosphorus that we got. So the phosphorus that was in the topsoil was retained there.
Well, I'm afraid I have to disagree with that, because if you take the data that are present in this table that we have just discussed, you also present iron ox and aluminum ox data, You can quantify how much fatty hydride is present, you can quantify how much gibbsite is present, and if I make this calculation, then the system is dominated for 60% by aluminum oxides.
Yeah.
So aren't you overlooking the role of aluminum oxides in this specific soil?
I think it's a very good point, and I agree. Probably now that I see the numbers, and yeah, we made more focus on the iron oxides, but it's true that it's already proven that the aluminium oxides also have power to retain and capture the phosphorus. So this sink of phosphorus that we were seeing in the subsoil is true, that we focus it more on iron, but aluminium also plays an important role in the capture of the phosphorus.
Okay,
Thank you very much. Your next opponent is Professor Bouwman from Utrecht University.
Dear candidate, first of all, my compliments with the work you present in your thesis, which is a nice combination of experimental work and modeling. And I wanted to talk a little bit about modeling. My neighbor already started about the machine learning. And in chapter 3, you write that the relatively low acceptance of machine learning in some environmental sciences may lie in reluctance to shift from a process-based approach to a data-based approach. And so this suggests that these researchers who use process-based models have kind of emotions that make them not work with machine learning approaches, or is there some other reason why they don't?
I see the point, and maybe it came out when I wrote it to be a more emotional decision, but I think it's also a reasonable decision, as we discussed before. It's not really. We have a lot of knowledge of processes already and how processes work. So to leave all that behind and only see with sometimes few data what you get, yeah, it's not always the best option. So sometimes it's for some objectives more trustworthy to see the processes behind. What we were focusing in was other small processes, for example, the gap filling, that was only one objective, to use the data to complete the data series. So that wouldn't be for forecasting or predicting what would be. In that case, I would still be on the side of these scientists that still recommend the process-based models.
Thank you. And let's then move to a more general topic. That is, the Netherlands is in a nitrogen crisis at this moment. It was already mentioned. And the focus is completely on air quality, on emissions and deposition on natural areas. And my question would be, if this approach would also focus on water quality, what would be most critical, water quality or air quality? What do you think about this?
For phosphorus, you mean, or for nitrogen?
Nutrients in general. I think phosphorus is an important one. But
yeah. So I think, yeah, there are different processes involved. Phosphorus in particular is not present as a gas, so the gas deposition would not be an important issue. It would be, yes, the transport through water, through dissolved phosphorus, and also in particles through erosion. So that wouldn't be, I think, the two most important processes. So the leaching phosphorus through the water phase and the soil particles. So those would be the two largest streams. In nitrogen, I think also are different effects being caused. Mainly the nitrogen gas. What I understand, it was focused in the greenhouse gases and the global warming effect. But in the water phase, what we would focus would be on eutrophication and water quality. So other amounts probably are needed and other limits also. Yeah.
thank you. Then my next question is the data that you show in chapter 2 and 3. Often we use a critical value for surface water quality of 0.1 milligrams per liter. And the data that you show in your chapter 2 and 3 point to a much lower phosphorus concentration than this 0.1. So the concentrations are pretty low. So I was wondering, why did you focus on phosphorus while nitrogen is super high in this drainage water?
Yeah, that is a good question. So what we, and it's true, I totally agree. The phosphorus levels in that farm are not particularly high. We didn't use the farm because the values of phosphorus were particularly high, but because of the disposition of the farm, because it was a really nice place to get good measurements. And it was a place that the farmer agreed to put the high-frequency monitoring station, and all the water was drained to one particular ditch where we could collect all the water. So it was not particularly selected because of the high quantities of phosphorus, but because of other things that the farm could give us, that was a possibility to have the high-frequency measurements.
Well, if you look at the data, then the molar ratio between N and P is about 700, which is extremely high, and that may lead to some other problems in water, like harmful algae, for example. Is there any way you have been thinking about these ratios or the relationship between nitrogen and phosphorus in the drainage water?
Yeah, that's a very good point. What we saw from the data, again, that it was only 4 years and probably more data is needed to get into conclusions and understand better the processes. But for example, on the last year, when the groundwater level was higher because water measures were taken by the farmer to retain more water inside the farm, then the ratio changed a bit slightly. So then we got more phosphorus and less nitrogen. So probably water retention can have an impact. So there are things that can be done to change that ratio. But again, probably more research is needed to be sure that that would happen always and in many farms and not only in this farm, particularly for that year.
Thank you. Then there's another question about the models. I was very much wondering when reading chapter 3, what would be the criterion for selecting a model? What is the quality that is required for a model? Because you have several, you have the R squared, the mean absolute error, root mean square error. So,
the committee will now withdraw for further deliberation. The session is adjourned. I hereby reopen the session. Madam Doctoral Candidate, this committee, installed by the Board of the Conferral of Doctoral Degrees, has considered your dissertation and has heard your defense. The committee has decided to confer on you the title of doctor, and I kindly ask the supervisor, Professor Middelburg, to invest you with the honors in the traditional fashion.
By virtue of the authority conferred on us by law and according to the decision of the Board for Conferral of Doctoral Degrees present at this session, I hereby confer upon you, Maria Victoria Barcala Pailio, the doctoral degree to which are attached all rights and obligations towards science and society as laid down by law and custom. Do you promise always to perform your duties according to the principle of academic integrity, honestly and scrupulously, critically and transparently, and independently and impartially?
Yes, I promise.
Then I present you with the diploma designed by the rector, supervisor and co-supervisors and bearing the Great Seal of Utrecht University.
Thank you, Professor Middelburg. The laudatio will be spoken by Dr. Oste, who was your main supervisor.
Zeer geleerde Dr. Barcala, dear Victoria, it's really a pleasure to congratulate you with your degree of doctor, and I would also like to congratulate Manuel, your parents, other family and friends. I'm speaking on behalf of Jack and Thilo, but also on behalf of Stefan and Joachim. Although they are not in this part of the room, their contribution to field work, but also to the scientific content, was really valuable. The combination of the academic environment at the university and the applied Deltaris projects created an excellent mixture for a successful PhD, but only because of your ability to benefit from these opportunities. You were able to integrate the knowledge, the experts, the data, the field sites into a broad thesis which includes field studies, lab experiments, modeling and machine learning. Your PhD position was part of the PTREP project, an EU project in 7 European countries on preventing the export of phosphate from diffuse sources into surface waters. You were a very active member of the PTREP community in, unfortunately, mostly online meetings, but also in schools, trainings on non-academic skills. The first blog on the PTREP website had been written by you, and you have been contributing most of the content since then. Working together with you was a pleasure because of your friendly, open and warm attitude. This enabled you to connect with a variety of people, from researchers to students to lab technicians and to farmers. People who worked with you experienced a lot of fun. Your ability to connect with various experts is also visible in the diversity of co-authors, varying from advanced modeling with the guidance of Orana Tseg and to microbial lab work in cooperation with Jan Gerritsen and Andreas Veugeling. During your secondment at Arcades, you also contributed to the practical applications of iron-coated sand, having nice names like Fatman and other installations. Fieldwork is important for understanding phosphorus transport in the Dutch agricultural landscape, in which at least the dairy cows are similar to Uruguay. Victoria showed not to be afraid of long, cold and muddy days in the field, and even Manuel was deployed in a 12-hour sampling campaign in the Achterhoek. However, no worries about the food due to Victoria's great baking skills. All the work resulted in a complete PhD thesis that normally takes 4 years, whereas you only need 3. 3 of the 4 papers have been published already in sound scientific journals, and furthermore, suggestions how to apply scientific findings in practice will be published soon in Water Matters, a magazine for Dutch water managers. I think the secret of writing a PhD thesis in a 3-year period was speed and efficiency. You regularly amazed your supervisors with the high speed you adopted tools and tips and the speed of producing revised manuscripts, which we had to read. Efficiency was visible in your lab experiment, whereas many PhD students perform a lot of experiments that are never published. I think almost all of your experience found their way in one of your papers. Apart from your scientific skills, you are well able to present your work, and in the pitching competition during one of the courses you reached the finals, and at the IAHR conference in Athens, you won the Gerard Jerke Award for the Best Young Researcher. After describing your excellent results, I would like to go back to 2019. You arrived in the Netherlands and rented an apartment in Gouda together with Manuel. Shortly after your arrival, your parents visited Gouda and experienced Sinterklaas and Goudse stroopwafels. They were lucky because a few months later we faced COVID, isolating you, at least physically, from people in the Netherlands, but also from your family in Uruguay. Under these circumstances, it was wonderful that you were here as a couple. At the same time, it was hard for you that Manuel didn't have a job, particularly when it took some time to find a position. Fortunately, Manuel got a PhD position in Enschede in June 2020, and for this reason you moved to Deventer. The apartment was much smaller than in Gouda, and it was a challenge to work both at home, but you managed to do it. You find a nice community in Deventer, partly international, but also Dutch, if I'm informed well, and it is a very nice and lively Dutch town. And since you found a new job at Touw in Deventer, you can even cycle to work. What's more Dutch? Victoria, I will remember you as an extremely talented person. Your broad interests and capabilities will help you to grow professionally and personally, currently as a consultant in wastewater purification. I wish you, together with Manuel, a bright future, and I'm convinced that you will create that bright future. Hereby, I would like to give back the word to the chair of the session.
Thank you very much. Very learned Madam, on behalf of the Board of the conferral of doctoral degrees, I congratulate you on the honours which have been bestowed on you. I hereby conclude the session.